In this video series, we're looking at regression with mixed variable types, both categorical, which I discussed in the previous video, and quantitative explanatory variables. We're still working with multiple linear regression, so we're dealing with a single quantitative response variable. In a previous video series, the entire series was about covariates, but we're going to do a little bit of review right now. Covariates are variables that are simply covarying. That is, they're correlated with each other, and we can use regression with covariates to partial out variable effects. Let's take a little trip down memory lane. There was one video series in which I illustrated multiple linear regression with quantitative explanatory variables by modeling the number of physicians in small cities with a variety of variables, specifically the number of hospital beds in the small city, the income in the small city, and the density. And so, if you recall, we started out by looking at zero-order correlations, that is, the individual correlations of each of the variables with each other, including the response variable. All of those have correlations that are non-zero, so all of these can be considered as covarying with one another, or they're all covariates. So not only do we have a covariate in terms of the response variable, which is always the case in our models, otherwise we wouldn't be using the variable in the model, but we also have covariation of the explanatory variables with each other. As a result of that, when we created a model, here I see in this particular report that I constructed, that I created a model with the number of physicians being predicted by the number of hospital beds and the income of the residents. When we create that particular model, what we have to do is recognize that each of these coefficients, like the 0.032 here for hospital beds, is looking at the effect of hospital beds on the number of physicians while holding constant or controlling for income. And so you see later on in my report, when I come down here and did things like created confidence intervals, notice what I said. I am 95% confident that after accounting for income, an increase in the number of hospital beds in a city by one additional bed for every 100 residents is associated with an average increase of between 5 and 60 physicians per 100 residents. But the key that I'm wanting to point out here is I say after accounting for income. That is because there is a covariation of income and hospital beds. So anytime we have regression with covariates, what we're doing is we're partialing out, or in this case, holding constant or keeping out or accounting for one variable when we're talking about the effect of the other variable. And conversely, when we talk about income, we're talking about income while we're here accounting for the number of hospital beds. So regression is used to partial out. We got even more formal with that partialing out when we talked about covariation by learning how to calculate such things as partial correlation coefficients. That is correlations among variables after partialing out the effects of another variable. And we had both partial and semi-partial. Partial correlation is when we actually took the effect out of both of the variables that we're relating, and semi-partial, as the name implies, is when we're only taking out the effects out of one of the variables. And those gave us two different pieces of information about the value of a variable in a model. So I'm not going to go all through that again because I have a whole video series on that, but this is a reminder of how covariates work. Covariates can be categorical or quantitative. When I introduced the concept of covariation, we were doing it with quantitative explanatory variables, but they can also be categorical. Now, factors are uncorrelated with one another in balanced ANOVA designs. A balanced design is one in which you have the same number of units that you're observing within each of the levels of the categorical variable. Or if you have more than one categorical variable, you have the same number of units in each combination of levels of the categorical variables. When you have a balanced ANOVA design, the factors are not covarying with each other. Now, they should be covarying with the response variable. That's why we're including them in our model, because we do think that the levels of the factor are covarying with what is happening in the response variable, but they're uncorrelated with each other. On the other hand, if you have different number of observations in each combination of the factors, then those factors are covariates with each other. That is, the factors do covary. So I had one example. I think I still have it up here somewhere. Let's look and see. Yes, here it is. Let me go ahead and knit this. I had one example here in which we had the different levels have different numbers of individuals in them for the plain risk analysis example. However, that was the only factor that we were working with. And so the fact that this was an unbalanced number of individuals, we didn't have to worry about covariation with other factors because there were no other factors. But once you get beyond one factor analysis of variance, if you have an unbalanced design, then you just have to be aware in that unbalanced design that the factors are covariates not only with the response, but with each other in those unbalanced ANOVA designs. We have also seen in past video series that when you have covariance as explanatory variables in a model, variables that covary with each other, there's also a possibility that they interact with each other in terms of their effect on the response variable. That is covariate interaction, and that will be the topic of the next video.